Okay, in this video I'm going to continue on my tutorials on thermodynamics and statistical mechanics. This is video number 19 and I'm going to discuss the factorial function. So because this is mathematical, it is not necessarily part of my thermodynamics and statistical mechanics course. So you could be watching this if you're doing anything. So this is part 1 of 2, because in part 2 I'm going to do out the integrals explicitly, but in this particular tutorial I'm just going to assume that you're going to accept the integrals, as you'll see in a moment. And if you don't want to accept the integrals and you want to see me do them, look at video number 2. So I've defined the gamma function. So we say that the gamma function of n plus 1 is equal to n factorial, and this n plus 1 is important, and I'll speak about that later. And we define it equal to this particular integral. So the bottom line up front is that the factorial the gamma function generalizes the factorial to non-integers. Okay, so how do we start? Well, we start by making a few observations, and I'm going to show you those now. So like I said, if you don't accept these observations straight out, then look at video part 2. But if you do, well then we're good to go. So let's look at the following derivatives. Well, integrals and derivatives. Well, if you do this, you're going to get minus 1, you're going to get 1 over a. Now, if inside the integral, next time we take the first derivative with respect to a, we take ddA of both sides, but ddA of an integral is just the integral of, let's say, ddA. You can move it inside. That's just a pretty basic principle of mathematics. So what we're doing is on the left hand side we're bringing inside the derivative, and we're also, well, of course we're going to be differentiating on the outside. But let's ignore that we're differentiating on the outside for the moment and just do it via the integral. And what we're going to get is the first derivative with respect to a of e to the minus ax dx. And if you do this, you'll find that the answer is minus 1 over a squared. And if we take the next derivative, you might be able to see that. If you take the next derivative, d2 dA e to the minus ax dx, you're going to get plus 2 times 1 over a cubed. You'll see, of course, that I'm writing the 1 even though it's not necessary, but we'll see why in a moment. You probably guessed in actual fact because I'm talking about factorials. So the only way to find a factorial is by writing down all the figures together separately. So if we take the next derivative, we're going to get minus 3 times 2 times 1 over a to the 4. And I'll do one last one. Take the fourth derivative with respect to a. And the fact that I'm taking it with respect to a is important. You might have made a mistake in the past where I tried to take it with respect to x, and that of course doesn't work. Okay, like I said, there are some observations. Accept them if you like, and if you don't, look at my next video. So let's look at some other integrals. So let's look at this one here. What if instead I did the following integral? I integrated minus x times e to the minus ax dx. Well, I'm telling you, if you do that integral, you're going to get minus 1 over a squared. If you do the following integral, this time it's plus, so go minus to plus. Well, take a guess what we're going to get here. We're going to get plus 2 times 1 over a cubed. Now this time I'm going to integrate minus x cubed. And you know what you're going to get here. And finally, we're going to do it just to be complete. This time it's plus. It's going to come plus 4, 3, 2, 1 over a to the 5. So the point to note here is that the answer, the parity of the answer follows the parity of the integral. So where it's plus, this stays plus, negative, this stays negative. But notice that there's an oscillating plus or minus 1, and generally how we talk about this, how we calculate or account for this oscillation, is by doing a minus 1 to the n. So just note that for the moment. So just looking at the left hand side, okay, I'd like to generalize the left hand side in the following way. We can say that the integral from 0 to infinity of the nth derivative. The nth derivative. Well, that should be a total derivative, even though I've written it as a partial. If you look at it, like there is quite a simple pattern, and the simple pattern is that it's minus 1 to the n factorial divided by a to the n plus 1. That's the pattern. Okay? Now, the next thing is, if we also look, so we know that, we'll say all of these give us this particular expression. But this expression also accounts for all of these answers on the right hand side. Alright? So that means that this integral must equal this integral. Alright? And equals this here. Now, what we need to observe is that in my integrals in the green, although I've written in the fact that we have an oscillating minus and plus, I haven't accounted for it in some sort of minus 1 to the n term. So it's there, but I just haven't written it in. So in order for us to, we'll say, generalize this, in order for this, we'll say, this to actually equal this, we need to get rid of the minus 1 to the n term. Because the minus 1 to the n terms, I personally wrote in the answer each time, instead of having minus 1 to the n. Alright? So that means that if we get rid of the minus 1 to the n term, we have the following. We have that the integral of x to the n e to the minus ax dx is equal to n factorial over a to the n plus 1. Alright? And that's because I get rid of this oscillating term because I already wrote it in to the integrals themselves. And that's our gamma function, as you'll see. We're getting a factorial function. So let's come to the conclusion. So the conclusion is as follows, that the integral from 0 to infinity of x to the n e to the minus ax integrated dx is equal to n factorial over a to the n plus 1. Now, of course, we can set a to be any value whatsoever. So let's see what happens if we set a to be equal to 1. Sorry, now it doesn't fix this. So let a equal to 1. Well, if we set a is equal to 1, we get the integral still. And we get this, it's n factorial directly. So we're after generalizing the factorial as some sort of integral. You might wonder, why is this important? Well, think about what n factorial means. Let's say 5 factorial. It means 5, 4, 3, 2, 1. In other words, all of these are integers. What if I asked you to get this? Well, you can't in the conventional factorial, you can't do it. However, of course, you can plug it into an integral and get the answer. So that's why it's important. So what we say is, we call this particular integral the gamma function. Why we call it something so obscure sounding, I don't know, but we just call it the gamma function. So we define it as gamma n plus 1. We don't define it as gamma n. Why? I actually don't know. So I've tried my best to find an answer to why we define it as n plus 1, and the answer is I just don't know. So you have to accept that the gamma of n plus 1 is equal to n. Now it still equals this integral. So it's just a bit odd. Okay? It's just a bit odd. Now, why is the gamma function useful? Well, I said because it generalizes the factorial to non-integers. So that means, of course, that the gamma of n plus 1 is equal to n times the gamma of n. Because this is n factorial, of course. Well, that's actually, yeah. this n plus 1 is quite confusing. What if then we look at what happens if n is equal to 0? So we try and get the factorial of 0. So if you want to get 0 factorial, so we look at the gamma of 0 plus 1, which is equal to the gamma of 0, the gamma of 1, and that's equal to 1. So that means 0 factorial is equal to 1. And if I was to give an educated guess, I'd say that's why we define the gamma function as n plus 1 rather than as n. to account for this, to account for 0 factorial. So 0 factorial is equal to 1. And finally, the last thing I'd like to show is that if I want to get d over 2 minus 1 factorial, well, this is simply going to be the gamma of d over 2 plus 1, which is equal to d over 2 factorial. Alright? So this is just going to be equal to, so the gamma of d over 2 is going to be equal to, is equal to d over 2 minus 1 factorial. Now why is that important? In another video, when I do the multiplicity of an ideal gas, I need to use this expression for the dimensionality of, or in order to get an expression for the for an n-dimensional hypersphere. But look, that's not really important. I'm just showing you an example where we use it here. Anyway, not to confuse the issue, I'll get rid of it. So the point here is that the gamma function generalizes the factorial to non-integers, and it's this particular expression here. So, if you want to see the integrals on it explicitly, look at my next video. So thanks for watching, please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.